Kia ora koutou, this is question 5 from this year's school exam, and this is a complex numbers problem. And we had to take this complex number, so z is equal to that, and we have to show that the modulus of z is 2 cos theta and the argument is theta. Then for the second part, we had to prove that the real part of 1 over z is constant. So there were quite a few different ways to do this problem. I'm just going to do it one of those ways. There are a few creative approaches. Some of them worked, some of them not so much. Okay, so the modulus is of z is going to be the square root of this squared, 1 plus cos of 2 theta squared, plus sine of 2 theta squared. Right, don't put an I in there. Most of you knew not to do that. Before I do anything with that, I'm just going to clean that up and say that 1 plus cos of 2 theta can be written as 1 plus 2 cos squared of theta minus 1, which is 2 cos squared of theta. So 1 plus cos of 2 theta squared is equal to 4 cos to the power of 4 theta. And while I'm at it, sine of 2 theta squared will equal 2 sine theta cos theta squared, which is 4 sine squared theta cos squared theta. So I'm going to call this thing here asterisk with a circle around it. So star is equal to the square root of 4 cos to the power of 4 theta plus 4 sine squared theta cos squared theta. And I think if you've done your working like that, this is a very nice, clean question. We can now take the obvious next step of factorising out the 4 and the cos squared of theta. And we get cos squared of theta plus sine squared of theta. We know that that's equal to 1. So this gives me 2 cos theta, which I think is what we were asked to show, yep, as required. Okay, so we're done with that part. Now, what about the argument? Well, the argument is going to be the angle whose tan is sine of 2 theta over 1 plus cos of 2 theta. And from the work we've already done, that's 2 sine theta cos theta. And the denominator simplifies to give me 2 cos squared theta. And that's going to be tan inverse of sine theta over cos theta. Now, why is it safe to assume that cos theta is not equal to 0? Well, cos theta can't be equal to 0 because if we go all the way back up to here, we had negative pi on 2 is strictly less than theta, which is less than pi on 2. So if you draw that little bit of the cosine curve, it looks like that. Okay, so there's no issues with having 0 in the denominator here. And that gives me tan inverse of tan theta, which of course is theta as required. And I think that wasn't as required. Let's see, were we told that? Yep, we were. The argument of z is equal to theta. Right, and then on to the next part, which is to prove that the real part of 1 over z is constant. Okay, so this was how I did it. I just went 1 over z is equal to 1 over 1 plus cos of 2 theta plus I sine of 2 theta. And then I times by the conjugate over the conjugate. Right, now we're only interested in the real part of that. So the real part of 1 over z is going to be 1 plus cos of 2 theta over 1 plus cos of 2 theta squared. Now the whole reason why we do that multiplying by the conjugate is to get this to be real. So it's going to be plus sine of 2 theta squared. And we're basically doing very similar to what we had before. We've got 1 plus 2 cos squared theta minus 1 in the numerator, and here we've got 2 cos squared theta squared plus 4 sine squared theta cos squared theta. And I've just put a note from part 1 and what we showed before. So that leaves me with 2 cos squared theta over 4 cos to the 4 theta plus 4 sine squared theta cos squared theta. And you can see a whole lot of stuff's going to simplify away. We get 2 cos squared theta over 4 cos squared theta into cos squared theta plus sine squared theta, which is equal to 1/2, because cos squared theta plus sine squared theta is equal to 1. Right, and that was what we had to show, that 1 over, the real part of 1 over z was constant, so there's no theta in there. Okay, so that's that question done. I'm going to do question 6 separately and probably not till tomorrow, because I think that's enough for one video.